I have this as a possible slit separation. Should I be happy, annoyed? Is that a good answer? So when you say really small, that doesn't help me much. Slit separations are small.
Yeah.
That's less than nanograms, or nanometers.
So this is typically the size of a neutron. All right? This is typically the size of a neutron or a proton. You can't make a slit that small. The slits ultimately are made out of atoms. All right? What's the size of an atom? This is the nucleus. What's the size of an atom? On the order of 10 to the negative 10. Right? So if you ever get an answer that's on the order of 10 to the minus 10, you're talking atoms. So you should be alert to that. Flip side is if you tell me separation is 10 to the 12, that's the size of the solar system. Right? So the problem I got was a lot of you you did some things right, but you were careless in your exponents. So you got some really, really strange answers. And I'm not going to take out more points because the answer's silly than I will just because it's wrong. But I want to. No, not really. If I can do anything when you leave this class, I would like you to have some notion of the basic structure of the universe and life and all this kind of stuff. So, size of atoms, size of solar system, size of things that make sense. Yeah.
So what would have been the answer for what is the nature of light?
It behaves as a wave because nothing about interference can be explained by anything other than wave theory. But I talked about, guys, remember I talked about this quite a bit in the sense that I said one of the things that we've always wondered from day one was, is light a wave or a particle? And then along came the Young-Just experiment, and we had conclusive evidence that light was a wave because interference can only happen with waves. The only problem is about 20 years later we got incontrovertible proof that light is a particle because photoelectric effect can only happen with a particle. And so the fun is now we've got experiments that show two completely different behaviors. So it's really an important thing in physics, this duality, because it launched the whole thing with quantum mechanics, which we touched on briefly before everything's all said and done. But look, I'm not too hung up on it other than I just really want you to have, I would like to get inside of you some idea of basic numbers so that when you write a silly answer, you know it's silly. Because as I've told you before, if you write a silly answer and go, wow, this can't be right because I know this is the size of an atom, I would give points. Even though your answer is wrong, I would still give points for recognizing that you have a silly answer because that's part of science, knowing when you've got a silly answer. Okay, but I also realize that you're seeing this stuff fairly new and raw and all that other good stuff. So, I'm not quite sure where to go. The scores are not bad, but the average on this test is certainly not as high as the last test. It's a bit lower. Averages are still going to be fine. It's not like everybody's going down into a hole, but it's just not as good as last test.
You said you're going to have that grade slip?
Yeah, so last day to drop is a week from today. So when I hand back your test, I will hand back a slip with your points. So on Monday when I hand back the test, you'll get a little slip with all the points that you've got so far, so you know exactly where you stand. By the way, pretty much the only one of those things you can mess with very much at this point is your last test. Here's the sad thing about life. You can't really raise your homework scores, but you can sure lower them. If you stop doing homework from here to the rest of the semester, they will drop like a rock. If you keep working really hard, you can keep them right where they are. It's almost impossible to raise them at this point because we don't have enough points left to make a difference. But zero averages them really fast to bad. So don't stop doing homework, but you're not going to be able to get much out of your homework. I'm giving pretty much everybody in the class who actually attends lab and does the work full points. So, whoopee, that's only 100 out of 1,000 points, but still a whole letter grade, all right? So we're good there. So the last test is really your best thing to try to pull this together. And I'll give you a pretty good heads up on that, like I normally do with the test. But the final is really the only thing left that's going to make any kind of significant difference on your grade. Like I said, homework can make a difference if you quit doing it. but others. And don't get me wrong, I'm not trying to say that because of this test people are going to change by a letter grade or anything. It's just that a lot of you didn't do yourselves any favors. Yeah.
What was the average of the last test?
I don't carry that number in my head right off the
Okay.
top of my head, but it was, I think it was a B. I know, it was a letter grade B, more or less. This test is definitely going to be at a C, which is, and C is a big wide thing. It's probably going to be a high C, but it's going to be a C for the average.
Thank you.
All right. So that being said, I'm ready to roll. A couple of things I want to talk about is last time I introduced several really brain scalding topics, and one we did quite thoroughly, one we kind of just flew past. Remind me, what is time dilation? Say what? Yep. I mean, under what circumstances does time dilation occur? What does it refer to? All right, that's key. Dilated time is always larger than proper time. So in order for that to make sense, Sean, it's a good start, but if I don't know what proper time is, I'm not any further ahead. So help me out, what's proper time?
It's in the same location.
So it's when two events occur at the same location, all right? And it's the time between those two events, all right? So proper time is the shortest that time can be. All other times in reference frames that move with respect to that reference frame, in all other systems, that becomes a longer time. So what was the equation that we developed? That was sort of the punchline of all this, where I said, how does delta t relate to delta t sub 0, where this is considered to be the proper time? Delta t sub 0 is the proper time. What's the factor that relates these two? I just want a single lovely Greek letter that ties these together. Gamma. And where does it go? All right. So because this is the shortest and gamma is always 1 or bigger, never smaller, then this would make it true, because multiplying this by a bigger number will give me the time that's always longer than proper time. So now we have to work our way through this. What is gamma? 1 over the square root of 1 minus c squared over b squared.
Oh, B squared.
No, B squared.
Okay, how about that? If I can, yeah, I flunked my own class. All right, b squared over c squared. I'd love to tell you I did that to test you, but I didn't. I just totally made a loop. All right, been waiting tested all. My mind's gone south. All right, so guys, here's the thing. We often use this equation to say that means you can never travel faster than the speed of light. Why would that imply? Why would this equation imply that you could never travel faster than the speed of light?
To become, we screwed up negative number.
What happens when v equals c? You have 1 minus 1, and you're dividing by 0, undefined process, which implies that time would stop. And that basically means that it can't happen. If time stops, your life stops, right? Because if time, all of life depends on time, right? All the chemical processes in your body that burn your food, that keep you alive, it's a time thing, right? So the rate at which chemical reactions take place, it's like a clock inside your body. So and this is actually fact, if you were in a rocket ship moving past me, in my reference frame, you would be aging more slowly than if you were sitting across the table from me. All right? And you're going, well, how can you ever test such a thing? What they did was they got 2 jets, 3 atomic clocks. Now, atomic clocks can measure time to several, like about 9 decimal places. All right? They synchronized all 3 of these clocks. They put one on one jet, one on the other jet, and left the third one at the airport. And then basically what they had, you know what great circles are? Great circles, when you fly around the Earth, you fly around in a circumference that may or may not be the equator, right? So wherever you are, you actually fly in a great circle. It's the circle that includes the point you've got that's all the way around the circumference of the Earth. Rather than, like if this is a planet, don't do this. You do the one that cuts the Earth in half. All right? So basically what they did is they did this, from my understanding, they did this as close to the equator as they could, so they basically were going with equators, all right? And they had one jet fly one way around the Earth, they had the other jet fly the other way around the Earth, and they had the clock that stayed on the ground. So playing this game in your mind, were the two jets in the air, they both flew at the same speed, were they both in the air for the same amount of time?
Yes.
Where the equator, one flies one way, one flies the other? Why were they not in the air for the same amount of time?
Going with rotation.
Because one's going with rotation, is always playing catch up. The other's going against the rotation, so it's faster, right? The Earth turns out from underneath it, so it can make it around sooner. The reason for doing this is they wanted to have two completely different times for circumnavigation so that they could see whether the amount of time that the clock was moving was a factor. So you understand that one jet went one way, the other went the other way, and the one that went with the Earth's rotation was in the air a lot longer before it landed. When they got down, all three clocks were different. Both of the jets had a different time than the clock that stayed on the ground. So my question for you is, were they ahead or behind the one that stayed on the ground?
They were there, behind.
Why would they be behind?
Moving.
Right. So if I'm the guy on the ground and I'm looking at the clocks on the jet, do I see them running fast or slow?
Slow.
Okay, so you understand that's why they get behind the clock that's on the ground. They run slow. When you land and you're back on the ground, your clock is not as far along as it would have been had you stayed on the ground. And the one that was in the air longer was even slower. And they were slow by the amount that general relativity predicts. Not special relativity, which we're studying, general relativity, because since they went around the Earth, we have to factor gravity into it as well.
So, if time is about interval between two events, so imagine someone in the plane.
He actually landed younger than he took off.
Yeah.
I mean, if he had stayed on the ground. Not younger than he took off, but he did not age as much as he would have had he stayed on the ground. So the astronauts that went to the moon and came back were several seconds younger than they would have been had they stayed on the ground.
So if the person is in the plane, his or her perception of time, because you observe an event, and you find the interval and you perceive time. The guy who is in the plane itself, I mean, the brain acts the same way. So events happening.
Here's the thing that's a little, what makes this scenario kind of twisted is, we stay on the ground, we see the clock on the jet slower. The guy in the jet thinks our clock runs slower. So why at the end is it that the jet actually is the one with a slower clock? Because he's the only one who accelerates. So he accelerates to get up to speed and he accelerates to stop. And so during that time there's actually a shift in, so we don't accelerate, our clock stays fixed. He does accelerate, his clock actually gets behind. So for example, if you had an identical twin, and this one's used all the time, you stay on Earth, you send your identical twin out to explore the stars, and they go very fast. When he comes back, he won't meet you, he'll meet your grandchildren, because you have aged a lot more because you stayed on the surface. His clock literally ran slower. His biological clock, everything ran slower, so that if he's traveling in space at a high speed, when he gets back, everybody he knew is dead, and it's their descendants that he meets.
Just
like
Interstellar.
But how long would he have to be out?
But it have to be long. This is what I'm saying. He has to be going near the speed of light throughout, it'd have to be many years, but not as many years as you might think. And no, we're not anywhere near able to do this yet to send somebody out. But this is an actual thing. You can actually measure how much younger or how much older somebody would be if they stay or if they go. It's measurable.
So you're using this example as an exaggeration so that we can understand the fact that he is going to be younger than his twin.
I am using it as an exaggeration only in that we don't have this kind of a space right yet. So here's the honest truth. All the science fiction that you watch, if you actually could get the accelerations they talk about, you couldn't keep communicating with Earth because you'd always be talking to different people because they would have aged and died while you were doing your trip.
Wait, what? I don't understand.
Because their clock doesn't move, so it's not slowed down. Well, if you're sitting on Earth, you're not going anywhere. If you're in the spaceship accelerating, then relative to Earth, you're moving fast, therefore your clock is slow. Oh, by the way, if you want to understand it, good luck. I don't know that I can tell you what it is, but I can't wrap my brain around why it happens. It's what happens. And like I say, they did the experiment with the jets, and it's exactly what was predicted. We needed that because it's not a big difference, but because they had 9 decimal places on the time, they were able to actually see the difference, and it was the difference that's predicted by the theory of relativity.
I just don't understand why, if you're moving faster than Earth, you said, your clock would go,
Because-
wouldn't it travel forward rather than backwards?
No, because see, from my point of view on Earth, your clock is running slow because you're moving with respect to me. And the reason at the end of the day, the reason your clock is the one that matters is because you accelerate to get there and you accelerate to stop. So that actually, it's more complicated than what we're ready to talk about, but it actually does mean that you have a net, you have aged less. So you take a trip in a car, you're actually not as old as you would have been had you just stayed home. All right, but it's not by almost enough to measure. But it is, we can measure it for certain experiments. Yeah, but guys, the problem is there's other ways you die while you're driving cars. I saw some other hands while I was doing that whole spiel. Yes.
Going back to the same question. So imagine a pendulum swings, that's my time for measurement. And yes, I understand the fact, based on that simultaneity theory, that if I'm on the ground, I'll see the pendulum swinging slow. But the guy who is
You've got a pendulum in the jet.
in the jet,
Okay.
so the guy who's in the pendulum, I mean, in the plane itself,
Does not see it slow down.
doesn't slow down.
He sees pendulum on the Earth slow down. But the difference is the acceleration that got him up to that speed and the acceleration that got him back down. So we're not really ready to talk about that because that's general relativity. So yes, during the moments that we just see him passing by, we each see the other guy's clock is running slow. But when he comes back to my position, the only way that can happen is he had to accelerate, right? If someone goes past me at a high speed, he's not coming back unless he hits the brakes, turns around, and comes back. So there always has to be an acceleration involved in the guy that returns to my position if I don't move, and that's what makes his clock ultimately behind mine. And it's by measurable amounts when even just going to the moon. It's by measurable amounts. I mean, amounts that even pocket watches can measure. I mean, like, you know, they've got hundreds of seconds on their little timers. So yes, a trip to the moon at the kinds of speeds they go, I think I'm right in saying it's like a couple hundredths of a second younger that you come back for that trip. Which, who cares? You know, it's not going to give you a whole long life you hadn't planned on. But the other thing you need to realize is that for the guy who does it, he doesn't feel younger. Life passes just the same as it ever did. He just sees you getting old really fast and wonders why. Not really, I mean, but he doesn't understand why everybody has gotten old and died when he comes back, because for him, time did not slow down. It just felt the same. That's because everything about being alive has an internal clock. There are rates that our cells and the chemicals in our bodies combine and create energy, and that whole being alive thing is a clock.
So that's we actually.
So what happens, the entire rate of which the metabolism takes place in your body slows down from my point of view. That's why you're younger.
In a way, we are actually living clocks.
Yes, but I mean, that's absolutely true, or else there wouldn't be such a thing as an average lifetime if we weren't clocks. Right? Aging is, I mean, you look at books on childbearing and there are things that kids do at certain numbers of weeks. They have internal clocks. Certain things happen in the body on average at certain times. We are clocks. Everything is a clock of some sort. Even a rock, which is not alive, aging and turning into sand, is a clock. Age causes everything to change, and the rate at which that happens depends on your clock. So I know this is kind of weird, and it may not, it's not something you can calculate, but relativity doesn't make any sense if you don't sort of get some perspective on what I mean when I talk about proper length and proper times. All right, so this then, if I look at this, this tells me that speed of light isn't possible because it blows this up. All right, so this is the first hurdle. Now, that means that if we can go faster than the speed of light, then this equation isn't complete, just as Newton's laws weren't complete, and we've stretched them with this. There could, in fact, be another equation that's going to come out of some other study that shows that this also fails at some point. We haven't found that point yet. And here's the difference about science and almost every other field of study. When somebody like Einstein comes up and says, hey, here's how it goes, you are not only welcome to challenge Einstein, it's encouraged. Try to prove him wrong. Go for it. Go for broke. Many have tried, no one's succeeded yet. Right? If you can prove Einstein wrong, you'd be the king of the new hill.
Occasionally you see the articles in the popular science magazines. Was Einstein wrong?
Well, I mean, because people continue to challenge. The fact is that we still teach Einstein because nobody successfully challenged him. Yeah.
What is gamma again?
Gamma is the factor by which time stretches or lengths contract. So gamma is the factor by which the proper time is stretched. And remember, then I also told you that lengths contract. So gamma is the factor by which a proper length contracts. Okay? Now, one of your homework problems that they have a bunch of, I think they did something like quintuplets, and they send them all up into space, and they all take different trips, and blah, 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 blah. And they want you to rate them according to the year that they return to Earth. Meaning who gets home first, or what's the calendar year when they get back to Earth from their trip. And when you first look at it, you go, how can I possibly solve this? But what they give you is that their trip in their reference frame lasts 20 years, and they were traveling at 0.8 C relative to the Earth. What do you think I need to do to be able to find out what the calendar year is on Earth compared to what they think? So they all leave on the same year, so they don't ask you what the actual calendar year is, they just say which one comes home to the biggest calendar year change. All right, so let's just make up a couple here. So my question is, how do I find out who had the biggest time change? What is this number? If I'm the person in the ship, and I say 20 years have gone by, what is this number? It's the proper time.
Proper time for the guy.
It's my proper time.
Your proper time.
All right. So if I want to find out how much time has passed on Earth, what do? I say I take 20 years and I multiply by gamma, where I can get gamma by using this to my velocity. And I find out how much time passed on Earth. That'll solve the problem. You'll get right answers. But do you understand it's a stupid question?
No.
Because if I travel at this speed for 20 years, I'm not coming back. Right? This is only for traveling in a straight line. So if I've done this in a straight line, I'm not back at Earth. I'm really pretty far away at this point. So what they do say in the problem, fairly, is they say, okay, you get out there, and you say, okay, and you turn around, and that's a very tiny part of the journey, and then you come back. So that your speed relative to the Earth is the same for this amount of time. But just the way it's stated, do you understand that it's kind of a silly question, right? Because if I really traveled that speed in a straight line, which is what this equation is for, I'm not back at Earth. I'm quite far from Earth. But that's how you actually answer this question. And I still think it's a valuable question because it helps you see how off, what the differences in the two calendars are.
Why can't you come back to Earth after?
What I'm saying is that that doesn't imply it, because this says this only works for traveling in a straight line with no acceleration. So if I travel at 100 miles an hour for 10 hours, I'm not back where I started. I'm quite far away. I'm at my furthest point away. I haven't turned around. I'm in a straight line. I'm not back. All right, so I'm just saying it's kind of a naive thing to have said. All right, so where do I want to go from here? All right, so that's one of the homework questions. Now, the basic thing, guys, that we've talked about, I want to be sure. When I say time dilation, I want you thinking this equation. When I say length contraction, I want you thinking this equation. Gamma's the same in both of them. Gamma's always larger than 1. There are a few gammas that we use fairly frequently because they're so absolutely useful. All right? So gamma is typically going to be given as like some decimal, all right? And if I say gamma is 0.8, actually no, let me not do that. Let me do beta. Beta is 0.8 C. All right, so this will work better. So I'm going to say beta is 0.8 C. Let me look at how that does to gamma. This is a rigged number. So I have 1 minus 0.8 squared, which is what? 0.64, right? All right. So if this is 0.8 C, and I say 0.8 squared is 0.64 C squared over C squared, the C squareds cancel, and I get this. Okay, higher math. What does 1 minus 0.64 equal?
0.36.
It equals 0.36. Right? And what's the square root of 0.36? 0.6. Right? Or, so it turns out that this is a really tidy answer, and if I did 0.60, I get 10 over 8. This will happen fairly frequently because before we had calculators and all that good stuff, this was stuff we could do in our heads. All right? you've got calculators, so they won't always be tidy. But just be aware, these kinds of things happen fairly often. So I have a question that I like to run past you at this point, just because it makes your lives really miserable. So, I have a spaceship. So like a spaceship. That's okay, we'll make it a big spaceship. It's 1,000 meters long. And when I say that, it's at rest with respect to me before it takes off. So my question for you is that a proper length?
Yeah.
Yes. When something's at rest with me, with respect to me, the length I get is the proper length. If it moves, will it appear longer or shorter? Shorter. Everybody got that? It'll be shorter by a factor of gamma. All right, so a couple of things. So I see the spaceship, I'm here, and I see the spaceship going past me. All right, flying by. And as it flies by, how complicated do I want to make this? Not yet. All right, so actually, I see it going at 0.6 C. So I see it traveling at 0.6 C. How long does it look? So we come here, I told you if beta equals 0.6 C, which is the thing, then I know that gamma is 10/8. Or 8/10? 10/8? No, it's 10/8 because I divide by it. All right, so here's the thing. How do I get the length? I've got the proper length. How do I get the new length? I divide by gamma. So I have 1,000. I divide by 10/8. But when you divide by a fraction, it's the same thing as doing what? Inverting and multiplying. Does everybody see that turns into 800? Right? I invert, the 10 goes into 1,000, it gives me 100, you multiply by 8. So I can see how much shorter it is. Are you good with that? Okay, go ahead. All right, so we now have, we have this relationship that goes on between them. All right, if I were to go at 0.8 C instead of 0.6, so now instead of 0.8 C, what would the new length be?
600 meters. 600.
So the faster I go, the shorter it gets. Okay? All right. Oh, you're ready for it. We're just going to throw the whole bucket of water on you. So what we have, and I want to use this same notation, so I can find his notation. What it is, we have a nifty velocity transformation equation. Ah, there we are. All right, so he does use it. He does it somewhere. I do it. All right, so here's the thing. We have equations that let me see how time changes when something moves and how length changes when something moves. But here's what's complicated. If I've got somebody in the spaceship and they fire a beam of light to the front, or not light, let's say some particles that travel to the front at a particular speed, as they're moving, what speed do I see? And here's the thing that's tricky. If the ship is moving past me at 0.8 C and they fire a photon beam to the front that's also going at 0.8 C, from old physics, how fast would that beam look like it's moving to me? Since the ship is at 0.8 and for the people inside the ship it's 0.8, then I would add the two together and I'd get 1.6 C, wouldn't I?
Yes.
But that can't happen because nothing goes faster than light. So we have to develop a whole new equation to find out how the velocity's at. Yes?
Before you go further, I'm going back to the length contraction. Length contraction happening as long as other person is moving. As soon as it stops, what happens to it?
It's not as, because they can't stop instantly, as they stop, the length grows. I mean, each new velocity they have gives them a different length. When they're finally stopped, the velocity is 0, and I've erased it, but when v goes to 0, then I just get 1/1, it's the length it always was.
It actually gradually becomes longer.
Gradually is a relative word, as it's all relativity.
So if my eyes and the brain could perceive things as finely as I'm talking about, I would see it's actually gradually getting bigger.
Yes. All right. So what we need then is an equation that helps me figure out what's the velocity of an object relative to my reference frame compared to the velocity of the object in the reference frame that I see moving. So, how we do this is we say the reference frame that I'm in is the S frame, and the reference frame of the thing that's moving is the S prime frame. You with me? So, this room is my S frame. A bird flying by is not part of my reference frame, so I tie a little reference frame to it and say that's S prime. So the entire reference frame is moving at the particular velocity of the bird. You with me? All right. So what happens then, the equation that we get is that the velocity of the object in my S frame is equal to the velocity of the object in the S prime frame plus the velocity of the S prime frame relative to my S frame all over, yes, it does get fun, the product, V O S prime, V S S prime, all over C squared. The good news is, that's an equation it would give you, and it's pretty easy to sort out. It doesn't look like it at first, but let's just think what it is. So what I'm going to do is I'm going to come back here and I'm going to draw the astronaut, and she's firing a gun to the front of the ship with a velocity inside the ship of 0.8 c. I'm going to stick for now with 0.6 c for them, so I don't have the same numbers running around. So the spaceship is going to go at 0.6 c. She's firing a gun inside the ship to her reference frame of 0.8 c, and I'm here. So S is the Earth. S prime is the spaceship. V, 0 S prime, is the beam. You got it?
Wait, what? What's the prime?
So S prime is the spaceship, and the 0 is the object, in this case the beam. So if we look at that equation, I want to know how fast is the beam in my S frame. I know how fast the beam is in her S prime frame. I know how fast her prime frame is relative to my frame, and those are the same two numbers I have down here.
Yes.
So it's really not as bad as it looks. Well, yes it is, but it's not worse than it looks. Okay, so let's come back and sort of think that through. She's fired the gun, it moves to the front of the ship, I can figure out how fast it's moving. Let's do it. All right, so I want to know how fast is the beam in the S frame going to look, and based on what I've got, this is how fast the beam is moving in the prime frame. For my picture, what is that number? How fast does it move in the S prime frame? 0.8 c. So I have 0.8 c. Then, how fast is the S prime frame moving in the S frame? Which is how fast is the ship moving? 0.6 c. And then I have 1 plus 0.8 c times 0.6 c all over c squared. This is why we usually get the speeds in terms of c, because then it's really easy to cancel down here. So instead of saying here's the speed, we'll say it's point something times c, and it makes it easier. But if I hadn't done that, then you would just have to use whatever the speeds are and literally divide by the speed of light squared.
What was Charlie at 0.8 c again?
0.8 c is how fast the beam that she's firing is. All right? Now, this will help sharpen your wits. There is always a question like this on the test. All right? There